Hello everyone, this video illustrates how the District Lab H Simulation Studio software can be used to optimize the temperature control of a complex heating network. To do this, we'll load a simulation representing the behavior of a French district heating network with a peak capacity of 450 megawatt during the month of January 2022. This network is made up of 3 geographical zones, all hydraulically connected, but each with independent differential pressure management. The network is fed by 5 main production sites, some of which are at the interface between 2 geographical zones. Let's begin this analysis by observing some interesting temporal evolutions during the month of January. For example, the third graph from the top shows the evolution of outdoor temperature and the presence of a cold week during the first fortnight of the month. Outside temperatures dropped to minus 11 degrees Celsius, corresponding to the system's design temperature. The second graph shows the evolution of the network flow temperature, which follows a simple heating curve. The first graph from the top shows the evolution of power demand and power delivery at consumer level. Note that these 2 curves are superimposed here, attesting to the fact that the network is controlled without any consumer being adversely affected. This first graph also shows the temporal evolution of thermal power injected into the network, presented in light blue. The last graph shows the cumulative power to be generated site by site. It's also possible to observe the details of network operation at the consumer's level. For the purposes of this example, we'll be looking at the so-called 96V customer, since it's located in a tricky area of the network, characterized by the multiple and intersecting influence of several production sites. The last graph from the top shows the evolution of the influence coefficients of each site on the 96V customer. These trends show an alternation between 2 main regimes, namely a single influence from Biomax and a cross-influence from Paterne and Villeneuve. The differential pressure across this consumer is shown in the second graph from the top. The trend shows that this value always remains above a few bars, which is in line with the requirements. Finally, the first graph from the top shows the evolution of the critical temperature shown in yellow. A consumer's critical temperature represents the minimum network temperature below which the consumer's demand can no longer be met. By comparing this critical temperature with the primary network temperature at the consumer inlet, plotted in purple, it is possible to quantify the temperature margin, which in this example is very strongly positive. This suggests that this network could be operated at a lower temperature without impacting on head demand satisfaction. To confirm this analysis, we need to take a more global view of the situation. This is possible thanks to a so-called tabulated view, which presents results for all substations in the network, while also displaying statistical indicators. We propose here to present the first percentile of the temperature margin, that is the value that separates the 99% most advantaged consumers from the 1% least advantaged. Typically, at the time displayed, the District Lab H software calculates that 99% of consumers have a temperature margin of at least 16.5 degrees Celsius. Finally, to consolidate this result, we need to analyze the network's hydraulic constraints. To do this, we position ourselves at the moment in the scenario when outside temperature conditions are at their most severe. That is January 15th at 7 a.m. At this point, let's take a look at the state of the network via its dashboard. The values shown on the dashboard indicate that minimum and maximum network pressures are well within acceptable limits. In addition, the differential pressure across the production sites also remains within an acceptable range. When combined, these elements of temperature margin at the level of a single consumer, temperature margins at the level of all consumers, and satisfactory overall hydraulic conditions demonstrate a significant potential for lowering the temperature of this network. To sum up, this video illustrates how District Lab H Simulation Studio software can be used to analyze and optimize the operation of a district heating network. Thank you for your attention.